Some months ago, we were estimating which was the elastic bending moment associated to this cross-section indicated or shown in the blackboard. According to the request of some of the followers of the channel, today we are going to estimate what is the plastic bending moment for this steel shape. Welcome to Sergio's Structural Engineering. A brief summary for the parameters that we are going to use in our calculation. Here in the blackboard, for example, we have the dimension of the steel shape that we are going to study. Okay, this is the behavior of the steel represented as a stress-strain diagram. Okay, assuming a perfect elastic plastic behavior of the steel. Okay, and also we would like to highlight that in case of a non-symmetry for the section, that is our case, the elastic axis is not the same as the plastic axis of the cross-section. Plastic bending moment for a cross-section is the result of assuming that all the fibers of the section are plastified. Okay, this is the concept that is represented here in this stress sketch in 2D and 3D. Okay, as you can see here in red we have the compression stresses for the steel, and below the plastic axis in blue we have the fiber under tension that has to balance this red compression stress. The first action, okay, is to estimate which is the location or elevation for the plastic axis. And for that action, we are going to establish horizontal forces balance at a cross-level section. Here in the blackboard, we have the horizontal forces balance established for the cross-section. Okay, so we have here the horizontal forces for the top flange, for the web top, okay, in this area, for the web underneath the plastic axis, okay, and the resultant forces for the area of the flange. Okay, as you can see, all the factors are multiplied by the steel J limit. Okay, so it's a common parameter that can be removed for this equation. So in order to get what is the depth, okay, for the plastic axis that we call Y, okay, is just to operate this equation taking into account the areas of these elements. So we get the final resultant, the final result that is 38.33 millimeters. That is the elevation for the axis measured for the top of the bottom flange. The second step is to starting to estimate the bending moment. Okay, so we are going to use the elevation for the plastic axis, okay, that we have here, and it is so easy just to take in bending moments for each of the resultant forces, okay, from this plastic axis. Okay, as an example, we are going to evaluate which is the contribution to the plastic bending moment, okay, for the top flange. So that's the steps that we are going to follow. Okay, it's just to take in moments, okay, from the axis, the plastic axis, okay, to the resultant of the forces due to the top flange. For that matter, we need the resultant, okay, and the distance from these forces for the resultant to the plastic axis. Here we have the area, okay, for the top flange. Okay, we have here also the J limit for the steel, and then also we have here D1, that is the arm from the plastic axis. Okay, so if we multiply all the terms, we have that the contribution for the plastic bending moment for the top flange is equal to 541 kilonewton. In order to get the final value for the plastic bending moment of the cross section, we are going to express all the parameters in a tabulated way, as you can see in the blackboard. Here we have in this first column the resultant forces, okay, that is the area for the different elements, okay, of the section multiplied by the steel J limit. In this second column we have the arm, okay, that is the distance from the axis to the horizontal resultant forces for the top, flange, top wedge, etc. Okay, and we have in the third column the final contribution to the plastic bending moment for each of the elements. That is just multiply resultant forces per the arm. Okay, if we have making here all the summation for these terms, we get the final bending plastic moment for this section, that is rising to 976 kilonewton per third step and final step for the video. We are going to draw the bending curvature diagram for this section. Okay, so we are going to base the draw, the representation in the previous values that we get in our former video. I will say the elastic bending moment and the associated curvature for the elastic bending moment. Okay, one of the ideas I would like to transmit is that if we assuming that all the fibers of the section are plastified, okay, theoretically we get a infinite curvature for the section. Okay, that's the point represented here. Okay, and also I would like to highlight like the last topic. It is the shape factor of the section. That is the equation that related the plastic bending moment and elastic bending moment. In our particular case, in this particular case for the section, the value is raised to 1.3.
Please remember that this exercise is strictly theoretical. Current design codes for steel structures, such as Eurocode 3 or the American AISC, establish a classification of sections into compact and non-compact categories. Before assuming a plastic behavior for a build-up section, ensure that the slenderness limits set by the applicable design codes are satisfied. Otherwise, you may be designing the section on the unsafe side. We have reached the end of today's video. We hope you find the content useful. Don't forget to subscribe, give it a like, join to my community, or share this video with anyone who might be interested in the field of structural engineering. See you again very soon.